Hey guys, in this video I wanted to go a little bit more into some types of decomposition reactions. The nice thing about decomposition reactions is that there's actually a guide to the types of decomposition reactions that you're responsible for in the reference guide. Again, this is on page 6 of the reference guide, and you can actually see they list all the different types of reactions. You've got synthesis, decomposition, single replacement, double replacement, and combustion. All right. So on any test, you're allowed to use this. All right. So in some ways, it prevents you from having to memorize quite so much. What we're going to focus on in this video are these decomposition reactions right here. All right. So one of the decomposition reactions, and the most common, is the one that we've already done, which is A, which is just a binary compounds, something made of two elements that break apart into their individual elements. All right, but what I'm going to focus on in this video is recognizing these additional types of decomposition reactions. All right, so one thing about decomposition reactions is that they're fairly easy to spot, and that's because they're the only reaction where you have only one reactant. All right. Notice that on all of these generic reactions, you only have one thing on the left side. All right. Everything else, like for example here, the single replacement, you've got A plus BC. All right. You don't have any something plus something else over here. You just have one compound. All right, so when if you were to see this on a test or a quiz, you would realize that there is going to be no such thing as no reaction. All right, if it asks you to do this as a decomposition reaction where there's only one thing, there is going to be a reaction. All right, so what I'm going to do here to go over these is put these on a separate sheet and go through each of them individually. All right. The reactions that are shown here are all generic reactions, and what we want to do is show how they can be treated as specific reactions. So the first one we're going to do is this one called metallic carbonates, which they generically represent as this right here. And for all of these reactions, we're going to do them the same way that we've been doing a lot of the other ones, where that same step of write things as a word, as names, then as a name reaction, then convert all those chemical names into chemical formulas, and then in the last step convert the chemical formulas into a balanced reaction. All right, so this is what is given to you in the reference guide. All right, but what I want I actually prefer for people to think about this instead of as a generic formula reaction where M just stands for a metal. All right, so by the way, there is no M on the periodic table. M stands for metal. All right, what that stands for generically is metal carbonate. All right, M is for the metal, and CO3 is that polyatomic ion, which is carbonate. All right, so this just stands for a generic metal carbonate. All right, so pick any metal on the periodic table, like sodium carbonate. All right, it could be calcium. All right, calcium is a metal. Any of those that are metals on the periodic table, put that word in front of carbonate. That's what this would stand for. All right, MO stands for metal oxide, and CO2 specifically refers to carbon dioxide. All right, so let's do this for a specific example. All right, let's say that we've got sodium carbonate. All right, and so the problem that you would be given would just be sodium carbonate with an arrow. All right, and you're supposed to figure out, well, what would happen. All right, well, we can see here from the data from the reference guide that a metal carbonate, and sodium carbonate is a metal carbonate, will break apart to a metal oxide and carbon dioxide. All right, so again, what I strongly suggest that you do is instead of trying to write down the formula first, write it down as the word first, the chemical name first, and then convert that into a formula, all right? Because you can't just substitute the elements in here and it be correct every time, whereas you can substitute the names into the word equations and that be correct every time, all right? So, oops, I made a mistake here. So the metal oxide version of that would be sodium oxide and carbon dioxide. And what we want to do is turn this word equation into a formula equation. All right, so in order to turn these to determine the formula, we have to apply the crisscross rule. All right, these are both ionic compounds. So sodium makes a +1 ion. Carbonate is this right here, which you could, and again, these polyatomic ion formulas are on the reference guide. All right, here we have sodium and oxide. All right, and these are the ions that they have. And for each of these, we're going to apply the crisscross rule. All right, so the crisscross rule for these ions will give us this formula right here. All right, applying the crisscross rule for these right here would give us this formula. And carbon dioxide, we're just going to bring that down. All right. The last thing you need to do is to check to make sure that the formula equation is balanced. Sometimes it might already be balanced. All right. If it is already balanced, what I want you to do is to make sure, that you put ones in front of everything. And that communicates to the teacher that you understand that this thing is already balanced. All right. If you leave the answer like this, I can't tell whether you knew that it was balanced or you just forgot to balance it. All right. So on the test, you would be expected to put ones as coefficients to show that it's balanced. All right. So the next equation is what happens when metallic hydrogen carbonates decompose. All right. Generically, we could represent it like this right here. So I'm going to take this reaction right here. All right. So this is that generic reaction. All right. And so what I recommend is first what you do is think of this not like it's a formula. All right. Because sometimes, for example, you can't just take any metal atom and put it in here and it would be correct. All right. What is always correct is to say that a metal hydrogen carbonate would yield a metal oxide plus water and carbon dioxide. All right. So let's give a specific example of this. Just pick any metal and substitute the word that metal for where it says metal here. All right. So potassium is a metal, so we could say potassium hydrogen carbonate would yield potassium oxide plus water and carbon dioxide. All right. So what we want to do is we want to take these words and put them in, make them formulas. All right. So again, to get the formula for this compound, we're going to need to know the ions and apply the crisscross rule. We would get this right here. Taking these two ions right here, all right, which we get just from the position on the periodic table. Applying the crisscross rule, we get this formula right here. And then we're just going to bring down the other things that are in that generic equation. All right, water is in there and carbon dioxide is in there. All right, this actually gives a good place to explain why you don't just substitute elements from the periodic table. Notice that in the first case, it is just a simple substitution of that M, which is generic for metal, with an actual element. All right, but notice that it's not just KO, it's actually K2O. All right, so if you write it down, if you consider this just to be metal oxide, convert that to the words potassium oxide, and then convert that into the formula, you'll get it right. Okay, so This is unbalanced though, and from this point, it's just a matter of balancing this, and you would figure out that there's a 2 here, there's a 2 here, and this would be the correct balanced equation. Okay, let's look at the next one. The next one is a metallic hydroxide, which would decompose into a metallic oxide in water. So again, taking the generic formula reaction from the reference guide, convert those to a word generic equation, and then substitute the metal in for the word metal. All right, so we're going to do this with calcium. All right, so calcium hydroxide should yield calcium oxide plus water. All right, taking these two formulas right here. So calcium is +2. Hydroxide you could get from the polyatomic ion list is this right here. Remember, when doing a crisscross rule with a polyatomic ion, put the elements and the quantities of elements inside the parentheses, put the charge on the outside of the parentheses, so that when you do the crisscross rule, you'll have something like this. And in this case, we have to leave those parentheses in because there's 2 of that polyatomic ion. All right, crisscross rule on this one would give Ca2O2, which gets simplified to a 1-to-1 ratio. So it's just CaO. And then you just bring down the thing that's also part of it. All right. So notice again, this would not end up being just a matter of substituting a metal symbol into this equation right here. The first one, you actually have 2 hydroxides in it. This is the actual formula. And I think it's actually a little bit misleading when you represent it like this, because it looks like it should always just be some metal with a single OH. All right. If this were potassium hydroxide, that would be the case. But if you're with the alkaline earth metals, the group 2 metals, it's going to have 2 hydroxides because of the results of the crisscross rule. All right. So taking a look at this, we want to make sure that it's balanced. We count up everything, and this one would be balanced. All right. The last example is represented generically like this. Again, the generic word equation would be a metal chlorate will yield a metal chloride plus oxygen. All right. So substitute in for a specific metal. We'll just choose potassium. Potassium chlorate would yield potassium chloride plus oxygen. Figure out what the formulas are by applying the crisscross rule. For these, we get this right here, KClO3 would yield KCl plus O2. And then you want to check to make sure to see if it's balanced. And when you balance this equation, this is what you would get. All right, so let's take a quick look at some of the problems that you had and see if any of these were on those decomposition examples. All right, so if you take a look at this reaction right here, this is the example. This is a metal chlorate. All right, so that is the last example that we did. All right, this barium carbonate, that is a metal carbonate. All right, so you should be able to find that generic equation. This is a metal hydroxide. You should be able to follow the example and do that one. Here's another metal carbonate. All right, sodium fluoride, that's the same type of binary one where they just break apart into their separate elements. All right, aluminum chlorate. All right, that's a chlorate reaction, a metal chlorate, and then another metal hydroxide example. All right, so I need to go back, try doing these, and I will be providing the answers to these soon. So give those a shot, and we will talk a little bit more about those later.